All right, thank you for the nice introduction, Koji, and also from my side, welcome to the attendees. And yeah, I'll try to give you a rough exposition of what we are doing in terms of dark matter searches at the LHC. Of course, it can be complete, but I'll try to be as complete as possible. I think just to remind ourselves why we are here in this conference, let's just point out that what we know and what we understand from the particle physics perspective are 15% of matter in the universe, whereas 85% is dark matter. And I show here also the two plots which show my favorite evidence for dark matter. I have no time to go through them, but feel free to ask me afterwards. Okay, so particle physics. So this is the first Feynman diagram already on the third slide. So mission accomplished. So the way we look for dark matter is essentially using this Feynman diagram here. And starting with direct detection, for instance, using the experiment xenon 1 ton or lux or something like this, we read this Feynman diagram with the time axis going upwards. So essentially we have a scattering of a dark matter particle of a fermion, for instance, from the target, and we register recoil. Now, what we can also do is indirect detection. So essentially we'll now let the time run backwards. So now we have two dark matter particles annihilating into a pair of fermions, and this is what indirect detection experiments are looking for. And that's precisely the inverse process of what we are doing at the LHC. So at the LHC, we are looking at the process where two standard model fermions, for instance, two quarks from the LHC, proton-proton collisions annihilate and give us a pair of dark matter particles and something else in addition. So this will be the focus of our presentation, or of this presentation. Moving on, what is the generic signature? So since we have attendees who are not really collider physicists by training, I want to explain this a bit more in detail so that everybody can follow. So if you look at this model of the ATLAS detector at the bottom, we want to look at the transverse plane. So the assumption that we make that there is energy conservation in the transverse plane, which is shown here on the top right. And if you are producing dark matter particles, they'll be carrying away momentum, which we will not be able to register since it's dark matter. We can't see it in the detector. This is the basic assumption. And this dark matter, this missing transverse momentum due to dark matter presence will be recoiling against some standard model objects, which can be, for instance, a jet, a Higgs boson, or yet something else. So this is the generic signature that we are looking at. Now, a rough exposition of models that we are using. So I've ranked them roughly by order, by their complexity and also by the richness of the phenomenology that they predict. So on the very left, we have effective field theories, where all additional degrees of freedom are integrated out. And we just look at low energy effects of that, so to say. Then we have simplified models, which are essentially well, one step beyond effective field theory. So we are looking at we are looking at them as signature generators. So we are looking at, for instance, a gluon recoiling against dark matter particles and things like that. However, these simplified models are typically really just signature generators, so they're not complete. And this brings me to the third category here, which are simplified, consistent, and UV complete models. So they're a bit better theoretically motivated, and also they can give us additional interesting signatures, which models in the second category are not so easy to provide with. And then the fourth category are really the complete models, and the most prominent one of them, which you're all familiar with, is supersymmetry, which often provides a dark matter candidate if R parity is conserved. So yeah, if you want to rank them in terms of kinematics, rich kinematics and phenomenology, it increases from left to right. And the focus of this presentation today are essentially categories 2 and 3. So we're really taking this signature-driven approach, and we say we want to turn every stone when looking for dark matter at the LHC, and these are the models that we are using to guide our searches. So I'll give you a rough exposition of what is being done at the LHC for these two type of models. So let's talk about the simplified models first, category number 2. And this is schematically represented in this slide. So we have here our standard model sector on the left. We have the dark sector on the right, which you remain completely ignorant about, except postulating one dark matter particle. And we have also a mediator, which then mediates between the standard model sector and the dark sector. So this is then generating the generic signatures that we are looking for. And here, as a representative example, I want to show one of the workhorse models at the LHC, which is also endorsed by the LHC Dark Matter Working Group. So this postulates an S-channel mediator, which is either a vector or an axial vector mediator. So this is also why we call it a Z prime, with a subscript V or A for vector, axial vector. And there we have actually a very interesting interplay between signatures. So on the left-hand side, we have the standard X plus MET signature, as we call it. So we have MET, which is missing transverse momentum due to dark matter particles escaping detection. And X is typically then one or several standard model particles. So in this case, it could be, for instance, a gluon from initial state radiation. What we are also looking for on the right are resonances. So if a Z prime boson, this mediator, was produced from a pair of quarks, then of course it can also decay into another pair of quarks, other fermions possibly. And so we are looking for resonances. And that's a very valid approach because in fact, half of the standard model was discovered by looking for resonances. Okay, so let's talk about the flagship analysis of X plus MET searches at the LHC. So this is essentially an analysis which is sensitive to many scenarios. The Feynman diagram is shown here on the right-hand side. So essentially we have here our quarks annihilating into as a prime mediator, which decays into dark matter particles. And because this by itself, you wouldn't be able to see in your detector, you wouldn't know that something has happened. You also postulate some initial state radiation has happened, which most likely is a gluon, simply because alpha S is the largest coupling constant. All right, so what's our selection? Well, first of all, missing transverse momentum, MET, larger than 200 GeV. Then, of course, we require a large transverse momentum jet from the hydrogenization of this gluon typically. But we also don't want to be too restrictive because we really want the signature to be sensitive not only to this particular model, but also to a plethora of other models. For instance, the inclusive squark production, which is shown here on the right. So essentially, we are allowing up to 3 additional jets. And the way this analysis works is that we are looking at an excess in missing transverse momentum. So we are looking at a number of events as a function of missing transverse momentum, and we see whether this agrees with standard model predictions. And just to help, just to guide your intuition, I have I'm showing here at the bottom right, just a mock cartoon of how typical event, candidate event would look like. So you have 2 protons coming in, dark matter particles, resulting in missing transverse momentum, recoiling against a jet. Okay, fair enough. So some eye candy here. So this is really one of the most striking event displays. We have here a jet recoiling against missing transverse momentum, shown in 2 different representations from the transverse view and also from the side. 1.9 TeV both. That's really a very nice candidate event. However, here comes the bad news. This candidate event can very likely be standard model. And one particle that really likes to decay invisibly in a standard model is the Z boson. It has a branching ratio into neutrinos of 20%. So this is then the Feynman diagram on the right. Our signal is on the left, so you see it's really an irreducible background. There's nothing you can do against it. And this is also represented here in these mock event displays at the bottom. You have missing a T, recoiling against a gluon jet. Okay, so how do we do it then? Well, the only possibility that we have is to really constrain the standard model background really, really well and measure it from a control region. So there we make the assumption, okay, fine. We have this background, but the Z boson doesn't care how it decays, whether it decays into charged leptons or neutrinos. So we use the decays to charged leptons in order to constrain this background. And this is what's shown here on page 12. So on the right-hand side, you have the distribution of missing transverse momentum in the control region with 2 charged leptons, electrons or muons. And then this is used to constrain this background in the signal region shown on the left, where we have the Z boson decaying into a pair of neutrinos. So all is great, but not quite, because the branching ratio of the Z boson in nature is unfortunately not in favor of this search. So the branching ratio to neutrinos is 20%, whereas the branching ratio into a pair of muons or electrons is 3% each. And this you can also see from the y-axis here. So what can we do? The next thing that we can do, the next best thing, is actually to use the one lepton control region. And this is shown on page number 13. So we essentially say, well, the W boson is almost the same as the Z boson, except for its couplings. And we can, in theory, calculate the differences between Z plus jets and W plus jets very, very precisely. And that's precisely what's being done here. So we use these calculations in this theory paper, which was also done under the guidance of the LHC dark matter working group. And we use the single lepton control region, which constrains W plus jets very, very well to constrain not only the W plus jets background, but also the Z plus jets background. So now, if you take our full data set of run 2, 139 inverse femtobarns, we are in a position to set very precise limits. And this is summarized here on slide number 14. So the limit plot from the analysis that I just showed you is here on the top right. This is the ATLAS search. And I'm showing here also the Feynman diagram just to help you memory, just to also help you match the masses of the particles in this diagram to the axis. So we have the mass of the mediator on the x-axis and the mass of the dark matter particle on the y-axis, which also explains why we are able to exclude things below the diagonal, because it's really hard to go above the diagonal because the mediator goes off shell. So yeah, in fact, you can see that our exclusion region is almost reaching 2 TeV. So that's very good news. And a lot of parameter space of this model is excluded. And CMS is also excluding a similar parameter space, similar region. And we are looking forward to the update of this measurement using the full run 2 dataset. What we are also doing is we are looking at the complementarity of our search strategies to those of direct detection experiments. And this is what's shown on the bottom. So these plots are typically represented in terms of the scattering cross-section of the dark matter particle with the nucleons. So on the right-hand side with the neutron, on the left from ATLAS, on the left-hand side with proton from CMS. These are 2 representative plots. They're more in backup and also in the publications, which are given here. So you're welcome to consult this for your favorite assumption. But the main message that I want to get across here is that there is very nice complementarity between the different search strategies at the LHC, but also in direct detection experiments, and of course, indirect detection as well. Okay, slide number 15 is showing one representative result where we have the resonant decay case. So here our mediator decays into a pair of quarks again. So this gives us a dijet event at leading order. And this is also how our event display at the bottom looks like. So you have 2 jets recoiling against each other in the opposite hemispheres of the detector. Now, in order to increase the sensitivity, we also want to include initial state radiation from both quarks. So this then is done by including additional jets if they're falling within a cone radius of 1.1 in pseudo-Euclidean azimuth of the higher PT jet. And also the standard model background, which is mostly T-channel dijet production, is being reduced by requiring that the rapidity difference of the 2 jets is not too large. And the search strategy is very simple. Like I said before, essentially all you do is you just look for resonance as a function of the dijet mass. Okay, again, a bit of eye candy. So this is the event display from the CMS collaboration, which shows 4 jets, in fact. So they are a candidate event under the assumption that one of, a pair of those, each pair of those 2 jets is essentially 1 quark and a gluon radiated of that. So we have here two dijet systems with 3.5 TeV balancing each other. This brings me already to the results on slide number 17. So you see here on the left-hand side the distribution in the dijet mass in a logarithmic plot. So you see that we're really exploring or probing a very wide range of dijet masses starting from 1.5 TeV. And what is done here is that the background is parameterized with a functional fit. And everywhere except for the region where you expect the resonance to be. And yeah, this allows us then to search for the signal in an unbiased way. Then as in the end, we get results as shown on the right-hand side. So let me explain you the CMS plot. We have here our Feynman diagram again. So on the x-axis, we have the mediator mass, and on the y-axis, we have the coupling strength. So the smaller this limit on the coupling strength, the larger cross-sections of new physics processes, the smaller cross-sections of new physics processes we can exclude. And at the bottom, you see also the ATLAS plot, but the common thing of those two plots is that they end at 1.5 TeV. So that's obviously a restriction, how to get around this. And the restriction is simply coming from the trigger rate or the immense event rate at the LHC. So one possibility to do this is to do a trigger level analysis, but even this brings you maybe to 400 GeV, but not further. So then the next thing is you actually use an initial state radiation jet to do the trigger. And that's shown in slide number 18. So it's essentially exactly the same type of analysis. You have initial state radiation, which is providing you the trigger with, with a very large transverse momentum of say 500 GeV. And then you're looking at the dijet system, which is produced in association with that. And since you're looking for very small masses, this dijet system will be strongly correlated. So you want to use a large radius jet in order to reconstruct it. So this is what's shown here on the bottom right. Well, the strategy otherwise is just look for resonance and estimate your background from data. So in fact, estimating background from data is not so straightforward here, but yeah, you're welcome to ask me how this exactly works in the questions. So the bottom line here is essentially that we are looking at the invariant mass distribution of this large radius jet. And we see here a very nice enhancement, this very nice peak from the W boson. We also have some contribution, well, W and Z bosons. We also have some contribution from TT bar. So we can actually test our search strategy by rediscovering the standard model. And so we are able to provide those limits as a function of the mediator mass down to 50 GeV, and with another analysis which uses photons as a trigger, even down to 10 GeV. So piecing this all together on slide 21, all the resonance searches, this is shown here in this plot. I don't show the ATLAS plot, it's in the backup, but basically the sensitivity is very similar. So you see that we are in a position to exclude couplings all the way down to about 5%. And of course, with the full data set and RON 3 approaching, we'll push that even further. Slide number 22 is showing another way of representing those results. So here they're shown as a function of the mediator mass and as a function of the dark matter mass. So not only the resonance searches are shown here, but also the X plus met searches. And for instance, the monojet search that I showed you at the very beginning is this yellow contour here. And the dijet resonance search that I just showed you from ATLAS is the one in light blue. Yeah, so you can really see how we can use the complementarity of X plus met and dijet or difermion signatures to constrain the parameter space. And this is only one of the scenarios that we are looking at. In fact, we are looking at more scenarios also in the backup. We also draw the parallel to direct detection experiments, which I've already shown before. But basically, the bottom line here is that there is complementarity in the sensitivity of the different approaches, which is very important if you want to cover all the bases. All this is done under the guidance of the LHC Dark Matter Working Group, which is essentially a forum to guide the interpretations of such searches and also their conception. So I just want to highlight this here because a lot of these interpretations were done under the guidance of the LHC dark matter working group. Okay, moving on to simplified consistent and ultraviolet complete models. So that's here on the right-hand side. So here we have a Higgs boson playing a special role. And this is motivated by the fact that the dark matter likes to couple to the Higgs as a probe. And here I want to show you the 2HTM plus pseudoscalar model, which is a simplified and ultraviolet complete model. And the nice thing about this model is that it provides you really a plethora of signatures. And I'm showing here the Feynman diagrams of only a few representative ones. And the most interesting ones are the ones which are bolded. So Higgs plus dark matter production, Z boson plus dark matter production, and TW plus dark matter production. And as a consequent, we also show the results in the masses, in the plane of the masses of the resonantly produced particle. So this is MA in this case, and small ma, which couples to the dark matter. And of course, tangent beta, since this is a 2 Higgs doublet model. Right. So slide number 28 is showing the first result from this domain. So this is Higgs decaying against dark matter. And in this case, Higgs is identified through its decays to dark matter particles. And this is shown here at the bottom right. We look for invariant mass of the diphoton system being enhanced as a function of missing transverse momentum. This is how the limit plots, the result plots look like. So you do actually see the standard model process, which is ZH production. And you can also see that the sensitivity of this analysis, which was just recently updated to the full run2 dataset, has grown considerably since the 36 inverse Runte-Barn analysis shown and overlaid here in blue. So now we are able to exclude an even larger region of parameter space. Now, the Z boson plus dark matter production works very similarly. In this case, of course, we look not for a diphoton system from the Higgs decay, but for a dilepton system from the Z boson decay. So we require that to recoil against missing transverse momentum. And here the results are very similar. So we are able to exclude a lot of parameter space because there is a slight deficit in data, and this is shown here in this result plot on the top right. So you see here the expectation in blue and the observation in red. So indeed, we are able to exclude large Higgs masses or capital H masses up all the way up to 1.2 TeV, and this is actually also a very nice improvement relative to the sensitivity using 36 inverse Runte-Barns, which is shown here on the bottom right. Okay, then a new kid on the block, which I really want to show you because it's quite interesting. So this is TW plus dark matter production. So again, this is resonance. So we have a charged Higgs boson which decays into dark matter particles, into W and pseudoscalar A, which decays into dark matter particles. And essentially, your selection looks for top quark, for W boson, and of course, for missing transverse momentum from dark matter. And there is a plethora of control regions which are introduced to constrain W plus jets production, TT bar production. We also use two different lepton multiplicities in order to enhance the sensitivity, because the top quark will decay both hadronically and leptonically, and the same also for the W boson. So here again, you have very nice sensitivity in the parameter space of the model, and you can exclude large portions of the parameter space. Okay, the dark Higgs model, I think I don't have time to cover. At the very end, I just want to talk about the Higgs portal models, 2 minutes more. So essentially now it's really the Higgs boson which couples to the dark sector. And this is really a nice hypothesis, because this is really the most minimal but complete model that we can come up with. And it's also an appealing fundamental interaction because the Higgs couples to the mass. So if the dark sector particles are massive, as dark matter must be massive, it's actually a compelling assumption that the Higgs couples to them. So here we can actually use the standard model production of the Higgs boson in order to guide our searches. So we are looking at different production modes: gluon-gluon fusion, Higgs-Strahlung, vector boson fusion, and TTH production. And what I want to show here is essentially the combination of all three searches. So I'll let you go through the searches in your spare time yourselves. And I'm going directly to slide number 43, which shows the combination of two very recent searches. One is in VBF topology, which is the most sensitive one from ATLAS, and then TTH, which is really the first time that this process is included in a global combination of Higgs to invisible searches. And indeed, this way we are able to push the limits on the branching ratio of the Higgs boson to invisible particles down, all the way down to only 11%. And this will become a single-digit number very soon. And of course, also in this case, we draw the parallel to direct detection experiments, and this is what's shown here on the left-hand side. This brings me already to the conclusion. So the bottom line is that dark matter is a fact. We are trying to turn every stone at the LHC. And in particular, we now started looking at more complex signatures now that our data sets allow it and we have lots of data. We use the Higgs boson as a probe. We also look at Higgs to invisible decays. And of course, even for run 2, not all the analyses have been published yet. So you should expect significant improvements from both collaborations, from CMS and from ATLAS. Okay, thank you very much for your attention.